Okay, so welcome back. So I wrote here kind of a summary of what we discussed yesterday. So I gave you a series of examples of problems, and what I was trying to say is that all these problems have in common that there is this rough landscape. So you want to minimize some function that looks like this, and so there are many local minima, and depending on the specific problem, you might want to find the ground state, so the absolute minimum, or maybe low enough local minima. And so what I mean, in the table I sketched up there, I tried to highlight the fact that in some cases, in most cases actually, the Hamiltonian or the cost function or the loss function depends on two kinds of variables. One are the variables that have to be optimized, so the degrees of freedom of your problem, and others are variables that specify the given problem. So for example, well, in the case of glasses, that was the first example, if you want to describe low temperature states, so glasses are low temperature states of your potential, the degrees of freedom are the positions of the atoms in the glass, so that's what I called X. And in that case, there is no additional parameter in the problem, in the sense that, okay, there is the potential, the two-body potential here, but this doesn't change from glass to glass. So if I take like this glass, or if I take this other glass, the interactions between the atoms in the two glasses are the same, so the potential is the same. This is kind of given by nature. But still, the two configurations of the two glasses are different. So maybe one is here and one is here in this landscape of minima. So in this case, there is nothing to specify. But in all the other problems that we have seen, there is some variable that specifies the problem. For example, in the traveling salesman, we have to optimize over all possible permutations of these cities that the salesman has to visit. And there are weights, and the weights are, for example, the price of the train ticket from city A to city B. And these, of course, depend on the set of cities. So one salesman will have certain prices, and another salesman that maybe work in another continent will have different cities and different prices. So you have to specify the weights on the set of cities, and then you want to optimize over the possible paths for that choice of weights, okay? But the weights are given, you don't optimize. And similarly, when you want to consider graph coloring, you are given a graph, so that's the input, and then you have to optimize the colors and find the configuration that minimizes this penalty that you pay every time there is a pair of sites that are connected, that have the same color. And similarly, in the problem of supervised classification that we have seen as an example of problem that you get in machine learning, you have to minimize this loss function, and the loss function depends on the variables that I call theta, that are the parameters, the weights in your neural network, but it also depends on this input that are the data that you have in the training set, so your set of images and your set of labels. So if you do it twice, you are typically work with different sets of images. So, okay, so these are all very, say, serious and important problems. So let's put the line. But then we said, okay, these are serious and important problems, but they are also very difficult. So let's try to start with something simpler. So let's try to have the simplest toy model we can imagine. And I told you that the toy model in this field is the P-spin glass. So the P-spin glass basically consists in saying, okay, let's keep the structure of the problem. I have some variables that I want to optimize. I have a disordered cost function with many minima. What's the simplest way of constructing such a function is basically to go on the sphere. We will see that it's convenient to go on the sphere because the variables are continuous. We already discussed it. And just let's put a Gaussian function on this sphere. We know that Gaussians are convenient to make all kinds of calculations, so that's the reason for this choice. The point is that, as I said, we want this function to be smooth enough. We don't want it to fluctuate too wildly. So what we want is that nearby configurations have similar energy. And that's why we want this Gaussian, to have zero mean. That's just a constant shift. But the important thing is that we want the covariance to be a function of the distance, so that configurations that are close by have big scalar product, and so the covariance is big. So I gave you the exercise of doing this calculation. I forgot an n, so I'm sorry about that. I hope you didn't spend too much time figuring out why the n was missing. It was just my fault. But that's the definition of the model. But in order to have a microscopic model and do calculations, we want to have an explicit expression for this function, and a convenient way of writing it is this one, where we do a linear combination of p-body interactions, Now, the last thing I wanted to say is that I will follow, so what I'm going to do today is to give you, without calculations, because I don't want to, it would take too much time to do all the calculations, but, so this model can be fully solved. You can solve it in 3 different ways. One way is to use replicas. So with replicas, you can get the thermodynamics of the model. The second way is to use dynamics. So you can do what is called dynamical mean field theory. And since I think most of you come from quantum mechanics, this is exactly the same as what is called dynamical mean field theory in quantum mechanics that you use to solve like the Hubbard model. The idea is to exploit the fact that this is a mean field system. As we discussed, all spins are interacting with all other spins, so you can think it's in a very high-dimensional space. And so you map the problem into an effective problem of one spin that is evolving in a thermal bath given by all the others, which is also the idea of the MFT in the quantum case, if you know it. And the last class of methods are kind of geometric methods where you try to classify the stationary points of this function. So you say, let's count, for example, how many minima I have at a certain level, how many saddle points I have at a certain level. So in all cases, you can do calculations. And the reference, I think, for this kind of, where you find all the details of these calculations is this one. This is these are lecture notes from Tommaso Castellani and Andrea Cavagna, where you will find all the details of these calculations. So what I'm going to do today instead is to follow these lecture notes that we wrote together with 2 collaborators, where we just give you, I will just give you the result, And tomorrow, maybe we can try to do some replica calculation on another model that is maybe a bit more general. We will see. So, so what's the behavior of this p-spin? Sorry, one last thing I wanted to mention is that, as it was pointed out, I think yesterday, this p-spin glass is also interesting in quantum applications. For example, you can study quantum annealing in this model. It's a good way to understand the difficulties of quantum annealing. And it's also, if the variables sigma are fermionic, then it's mapped into the SYK. And so for quantum, if you're interested in quantum versions of the p-spin, the reference is the work of Letizia Gugliandolo and collaborators, so you can, I can give you, I'm not sure that there is a review, but there is a series of papers where the quantum properties of the p-spin glass are studied from Letizia Gugliandolo, so if you look for that, you will find it. Now, okay, what we want to do is to study the thermodynamics and the dynamics of this model, and as we discussed yesterday, we want to study equilibrium dynamics, and then out of equilibrium dynamics in the case of gradient descent. So the dynamics I'm going to use is the Langevin one, so I will write it in this way. I will take over damped Langevin, so the time derivative of sigma component I is going to be given by the force, so the gradient of the Hamiltonian, minus an additional term that I will explain in a second, plus some noise. So everything here depends on time. Well, I will not put the time dependence explicitly, except for the noise that maybe sigma depends on time, of course. And the noise, as usual, is a white noise, such that the average here is given by the mean of the noise is 0, the noise is Gaussian, and the covariance is a delta function. Sorry. So, why do I add this additional term? I hope you can read. Maybe it's not very, okay. Why do I add this additional term? Well, because I want to stay on the sphere. So I want the norm of the vector sigma to be equal to n. So I have this constraint here. And so you see that this is, if I compute the gradient, then what I'm doing here, I'm just removing the longitudinal component of the gradient in such a way that I only keep the tangent part to the sphere. So this mu has to be determined self-consistently by imposing this constraint in such a way that the derivative of sigma is tangent to the sphere. We will see, it's a simple calculation, but we will do it at 0 temperature, so it's even easier. Okay, so this is the kind of dynamics we want to study. It's one possible dynamics. You can construct different ones, but what we know, okay, a general result that we know is that if n is finite, then this dynamics will always go to equilibrium, okay, with some mild assumptions. So for a finite size system, the distribution of sigma will converge to the Boltzmann distribution. The problem is that, depending on the situations, it might take an exponential time in n. So what is clear, is that if you wait a time that scales exponentially with n, you will always explore more or less the whole space, because the size of the space is exponential in n. So the question is whether we can equilibrate in a finite time that doesn't diverge with system size. Now, so before we go to the dynamics, let's take a look at the thermodynamics. So the properties of, yes?
Ricardo, just the hypothesis when saying that you have cloned the whole sphere.
Yes, but here we have noise, so it's basically a property of the, you have to assume ergodicity in the sense that you don't want your Hamiltonian, like for example, to have infinite, to have regions in the space where it's infinite, so you cannot go, but this is not the case. This Hamiltonian is a finite function. So essentially you can write the Fokker-Planck, you can look to the notes for details, but you can write the Fokker-Planck equation and then you can show that. Okay, so okay, let's start looking at the equilibrium properties of the model. So So this is the Boltzmann distribution. Well, I forgot to mention one point that, okay, of course, when we go from these problems above to the p-spin, we are forgetting all the structure that we have in the problem. Like if you have data and you want to do supervised classifications, your data are images, for example. Images have a certain structure, and here we are just forgetting about all that and going to a Gaussian problem. So it's a wild step, okay? And we can discuss later to what extent it's useful to do that. But so let's first look at the model. So, okay, this is the Boltzmann distribution. Now, there is one special case, which is the case where p is equal to 2. So if you set to 0 all the other coefficients and just keep the two-body interactions, then the model is kind of trivial, because the Hamiltonian, then it's quadratic in the spins. And since the spins are continuous, you can diagonalize the Hamiltonian. So you do a change of basis, and I mean, this is actually a GOE matrix because the J are Gaussian. So you diagonalize, and you get, in the diagonal basis, the Hamiltonian is just that of independent spins. The spherical constraint is invariant under rotation, so it will be conserved. So this is mapped into a problem of independent spins, and what happens in this case is that there is just one phase transition at a critical temperature, Tc, and above Tc you have a paramagnetic phase where all these sigma are positive and fluctuating, and below Tc you have a ferromagnetic phase where there is condensation in the lowest eigenvalue, okay? So you get two states that are just where only the sigma that corresponds to the lowest eigenvalue is populated.
So for the moment you are considering ferromagnetic?
No, this is true for, I'm considering Gaussian couplings. So the J are Gaussian with zero mean and variance given by the expression I gave the other time. So even if the J are positive and negative, this is a symmetric matrix. You can diagonalize it, so you get eigenvalues. And so if your spins are continuous, then you can just do, it's just a change of basis, and you get independent spins. The spherical constraint is just the constraint that this vector has a fixed norm, so it's invariant under rotation, and so that's it. So you get independent spins, and then what you will see is that what happens is that there is a temperature at which you just condense into the ground state, but that's it. So it's different from the case of, if these are Ising spins, then it's different because you cannot do a rotation in the hypercube, so you have an additional constraint.
What do you mean that the couplings J are Gaussian in what?
So each of the J is an independent Gaussian variable that has zero mean and variance given by, so in general, in the general case, the variance is p factorial divided by 2n to the power p minus 1. So in the p equal 2 case, the variance is just 1 over n. Okay? So I draw each coupling with this law. So they can be positive or negative. The distribution is symmetric. This is just a GOE matrix, right? Yes?
At least at the level of the MFT outstanding model, at the level of the field, every model with higher speed interactions can be reduced to such, in some sense, to such a case.
Why?
Because you can always companies say that all the other spin are just the average of all the other spin are just
No, you cannot do that. Yeah, I mean, it's not so simple. So you have to, I mean, there are correlations in the spins that are weak, but they are there, and there are many spins, so the two things compensate, and you cannot just map it on the...
What is the order parameter for that?
The order parameter, but for example, you can take the average of the average, I mean, the magnetization along the lowest eigenvalue. So these variables, I don't know why this thing is not stable today, but these variables sigma alpha are the projection of the projections of sigma over the eigenvectors of the matrix Jij. So these are magnetizations, but so in a usual ferromagnetic system, this vector would be the all one vector. So this is just magnetization. This is a disordered case where this is a disordered vector that depends on the J. But if you project along that thing, you will see that these projections are all of the order of 1 over n in the paramagnetic phase, I think. And then in the ferromagnetic phase, there is one that becomes finite. And of course, you have the other. So if this is the...
But if the couplings is just like random Gaussian variables, then it's not clear that you always be able to diagonalize the matrix, right? Because it can be any number.
It's symmetric. It's a symmetric matrix.
It's symmetric.
Yes, because I'm summing over I smaller than J and the coupling, because you see, if I have I can always, I mean, this Hamiltonian is the sum of a coupling times a symmetric thing. So, you know, like suppose I write it in this way. But then I can always symmetrize it, because I will do this, then I exchange the labels here. So this I write it as but now this thing is symmetric. Sigma I, sigma j, or sigma j, sigma I is the same. So this becomes the sum over I smaller than j, jij plus jji, sigma I, sigma j. And then I call this J, and it's symmetric. Okay, so I cannot construct a Hamiltonian system with non-symmetric couplings.
Just a follow-up question.
Yes.
Alexander's question. So what we're studying is really a distribution of models, right?
Yes.
We get a model for every possible values of the
Yes.
couplings, right?
Yes, except that yes, you're right. But what happens is when n is large, I have an ensemble of models. I mean, precisely as I was trying to highlight here. So for each given choice of J, I have a different model. But when n is large, they all behave in the same way. Like we know that GOE matrices in the large n limit, they have a well-defined spectrum. So in the end, the lowest eigenvalue is going to concentrate around its limit. I mean, the eigenvector is going to change from system to system. Okay. So the case p equal 2 is a kind of special case, which is basically a ferromagnetic model. So I'm going to forget about it, and so I will have to include additional terms with p bigger than 2. And so what we can consider as the simplest case is just fixed p. So for example, p equal 3. Okay, so in the p equal 3 case, my Hamiltonian is the sum over ijk of j ijk, sigma I, sigma j, sigma k. So what do I get for the phase diagram in this case? Well, there are two phases. So if I plot, for example, energy versus temperature, I will have high temperature phase that is kind of paramagnetic. And then I have a low temperature phase, which is a glass. And there is a temperature Tk, it's called Kautzmann temperature for historical reasons, that separates the two. This is the generic situation in all cases where there are more than two body interactions. You can have, if you tune well the coefficients, you can get more exotic situations, but this is the one I will focus on. So what's the order parameter for this transition? Well, in the paramagnetic case, what happens is that if you take the thermal average of any spin, this is going to be 0. Okay? In the glass phase, if you take the thermal average of a spin, it's going to be different from 0, but it fluctuates a lot because it depends on the couplings. This is also what happens for p equal 2. But also it depends on the state. So in the glass phase, there are many states. Like in a ferromagnetic system, there are two states, the plus and the minus. Here in the glass state, there are several states. And in each state, the value of sigma is different. So this is not very convenient as an order parameter. So what people did to take care of this is to introduce what is called the overlap order parameter, or Edwards-Anderson order parameter, because it was introduced in a paper by Edwards and Anderson, which is 1 over n. So let's say I take two independent copies of my system, sigma and tau. So sigma is in equilibrium with the distribution, with the Boltzmann distribution, and tau is also in equilibrium with the same Boltzmann distribution, with the same couplings, okay? This depends on the couplings. So I take two copies of the same system with the same couplings, and then I compute the scalar product of the two, and I take the average. So what happens? Well, I also take the average. I first take the average over the Boltzmann distribution, and then I can take the average over the disorder. So now this is a number that does not depend on the J anymore, because this average in principle depends on the J, right? The name. This has been introduced in a paper by Edwards and Anderson, where Anderson is the Phil Anderson that you know, and Edwards is Sam Edwards that probably you also know. So these are big names.
So for p being an odd number, it looks like you're indicating that you don't have parity inversion symmetry.
Yes.
There seems to me that there should be some difference between the odd and even.
Yes, you're right. So let's say that I'm always implicitly assuming that the inversion symmetry is broken. So if P is odd, fine. If P is even, I'm always assuming that I put a small magnetic field in the plus direction, for example, and I send it to 0. Because I'm not interested. So the point is, okay, I will get to that, but the point is that there are many glasses. So each glass state is a region in this space. Now, if there is inversion symmetry, for each glass there is a mirror one, but this is a kind of trivial degeneracy that I want to get rid of. If I put a small infinitesimal field, I'm going to break the inversion symmetry as usual in a ferromagnetic system, so I can only focus on half of them. This is not going to change, it's a factor 2 in the counting of states. But yes, you're right, so let's assume that there is a small, like H, sum over I of sigma I, and H is going to 0 plus, for example. Yes.
What was sigma and tau in your?
So sigma and tau are two copies of the same system. So I have my sphere. I have a probability distribution on the sphere. I draw twice a configuration from the same probability distribution. One is sigma, the other is tau. I compute the scalar product, and I take the average. And so when I take the average with the given Hamiltonian, this depends on J, and then I can take also the average over J.
If we are taking two Hamiltonian, then we are already taking an average of J. The two Hamiltonian will not have.
The sigma and tau are two copies of the same system.
Okay.
The same couplings. When I say the same system, sorry, I mean the same realization of the couplings.
Why would sigma be different than tau?
Two different spins.
It's two. This is a many-body configuration, but they are different. For example, in the paramagnetic phase, the probability distribution, the Boltzmann distribution is kind of uniform over the sphere. So if you take 2 points on a sphere at random, in a high-dimensional sphere, they will be typically orthogonal. Because if you fix one and you maximize the entropy of the other one, you want to be orthogonal. Okay?
Sorry, so here the order of the transition is...
I will come to the order of the transition in a moment. It's complicated. I have to do a bit of work to get there. It's going to be a mixed kind of transition. Bit of second order, bit of first order, but let me arrive to that slowly. So let's try to see what's the intuition on this order parameter. So if I am in the paramagnetic phase, so how can I write this? This is 1 over n, sum over I of sigma I tau I. This is the average, because I can factorize the average over J, right? Because the two configurations are independent by construction. And then I have to take this average over the couplings. Well, if the system is paramagnetic,
I mean, sigma I, are these the two vectors, or are these the two columns made of many vectors? Are these only one?
sorry, no. There is only one index. So sigma is a vector that has components sigma I, sigma 1, sigma n. Sorry if my notation is not clear, but... So sigma is a vector in n dimension on the sphere, and sigma I is the component I of this vector. Okay? So if I am in the paramagnetic phase, each of the two copies is going to be paramagnetic, so the average of the spin I is 0. So this thing is going to be 0, okay? If instead I am in the glass, what happens? For a given system of J, the spin I is going to be magnetized in some direction, okay? And then, but then also the spin tau is going to be magnetized in the same way. So if I call this magnetization Mi, that depends on the couplings, and it's different from 0, what I get here is 1 over n sum over I of Mi square. This Mi depends on the couplings. I have to take the square and I have to take the average over the couplings. Now, if I take the average over J of M, what you find is that the average is 0, because, in different realizations of the couplings, the system can magnetize in every possible direction, right? So if I take just the average of M, it's going to be 0. But if I take the average of M square, then I get a finite value. So this thing is going to be positive in the glass. okay? And so basically this Q is the, I mean, if the system magnetizes, then you take the square of the magnetization vector and you average that. So that's a good order parameter.
At the end of this order parameter is, since the average of each mi is equal to 0 independently, we can see it as susceptibility depending on the configuration of J.
Yes, so the, yes, Q is connected to a magnetic susceptibility.
Magnetic susceptibility, but the susceptibility depending on the, well, J, which is the.
So yes, the point is, so you can show that the magnetic susceptibility is something like beta times 1 minus Q, something like that. So it's, the two things are connected by, if you do a fluctuation dissipation calculation. But yes, I mean, for a given J, this quantity inside depends on J, then you take the average. The point is that this is a global quantity, is an average over all the spins. And so in the thermodynamic limit, because you have many terms, these terms are positive, there are many of them, the sum will converge to the average. So the fluctuations of this quantity from one realization of the J to another realization are small, okay? Yeah, I'm sorry, there are plenty of details that should be discussed, but I'm
Just another thing.
yes.
Could we view this J dependence as a temperature dependence or time dependence? I mean, these couplings, they are Gaussian, right? But they're
Yes.
Gaussian in what variable? In time, in temperature?
No, these are Gaussian, okay. Well, the problem is, okay, they are Gaussian in themselves, in the sense the idea is I first draw these couplings from this Gaussian distribution, I give to you the couplings, and now you have one Hamiltonian, and then you want to find, for example, the ground state of this Hamiltonian. So before we look to the ground state, the first thing you can do is, okay, let's do statistical mechanics. It's maybe easier, because at high temperature, maybe the problem is easier than just finding the ground state. Now I can draw the couplings again, and you have another system. So you have this ensemble of system. If you want to think in physical terms, then the idea is that, okay, I mean, historically, the spin glass materials are alloys where you have magnetic atoms that are embedded in a metal matrix. So you have this metal, this piece of metal, you have these magnetic atoms, the atoms carry spin. And the point is that because this is an alloy, you create it at high temperature, then you cool it down. The position of the impurities is frozen, because when you go to low temperature, this becomes a solid. So you have a solid metal and you have impurities. So the J, the exchange coupling between two given spins, depends on the relative position. And because the relative position is frozen, then you can take this to be some Gaussian, some random number. That if you heat the system up and bring it back again, it's going to be different. So if you want, then you can think that your disorder is kind of frozen in time. So the time scale for the evolution of your J is much, much longer than the time scale for the evolution of the spins. And so the random distribution is somehow over time.
I was having trouble just interpreting physically what
yes.
these sets of distributions of Hamiltonian means.
Yes, I agree. I didn't motivate it physically, because I just wanted to consider it as a toy model for this kind of problems where you are given some variables and you're going to optimize over other variables. But physically, this basically means that there is, in your Hamiltonian, there are some variables that evolve on a time scale that is huge compared to your experiment. So you consider them as frozen, and they are frozen, and they come from some distribution that depends on the way you prepared your system, like, for example, when you mix these magnetic atoms with this metallic.
Then you're always interested in the average of the possible J's, right?
We are interested in the average because we believe, and we can also prove, but I cannot do that when the system is large enough, a typical realization of the disorder is going to give you the same results. Sorry, let me say it better. I mean, the point is that if you compute some observable on this system, that is like an extensive or intensive observable, but it's a sum of many local observables, the fluctuations of this over the realization of the disorder are small. So when a system is big enough, like if I take this piece of glass and I measure the specific heat, or I take this one and I measure the specific heat, it's the same in the thermodynamic limit. Yes?
I scale questions, but if the system was ordered, we would expect this quantity to be, well, to scale like 1, because all the mi are equal. But here, since the system is, in some sense, disordered, the glass, what scale do we accept for this Q quantity? Do we expect it to be decreasing with the number of sites and going to 0 for large?
No. So, as you say, in a ferromagnetic case, if you compute this, you get 0 down to Tc, and then you get something like this. This is essentially the magnetization square, right? So this is what you get in a ferromagnetic system. In the spin glass, it depends, but so for example, in the case P equal 2, the one that has a ferromagnetic-like transition, you get exactly this. In the P spin with P equal 3, we get actually a jump. So at 0 temperature, Q is equal to 1, which means that spins are fully polarized in random directions. And at the transition, you get a jump. So now we have to understand why we get this jump. So it looks like a first-order transition, but we have to understand a little bit better what's going on. Maybe I should take a break, right? I don't know. I lost track of it. No, I started at 11:20. So in 10 minutes we can take a break. Is that okay? No. No, right. It's 50 minutes. Okay. Well, maybe we can take a break now, and before I move to the dynamics, because the next step. So this is okay. Let me just fix this. So this is the thermodynamics. You can solve it. You have to do a replica calculation that I don't have time to do, but if you want to look at it, it's here. You do this replica calculation because you want to do this average over the disorder, so you need replicas. But okay, the result is this. There is a high temperature phase that is paramagnetic where Q is equal to 0. All the local magnetizations are 0, and that's it. And then there is this first order looking transition at this decay where the overlap has a jump. So you generate some spontaneous magnetization in the system, and you get the glass. But this is not complete, so now the next step is to do the dynamics, which I will do after the break.
All right. Any questions? Right.
So we have seen the thermodynamics of the model, and I understand that you are very confused because it's confusing. So please keep asking questions, but I hope that if we now look at the dynamics, things become more clear, okay? So that's what I'm trying to do now. So how do I look at the dynamics of this system? So I have my vector sigma. So sigma is a vector of n components, n is large. I have my Hamiltonian, which is a function on this sphere on which sigma is evolving. And I want to make sigma evolve using this Langevin dynamics. And I know that at large times, this will converge to equilibrium. So what can I measure to have an idea of what's going on? Well, I have to measure some correlation function, okay? So what's a good correlation function? This is going to be hard. So I can define a correlation function in this way, and you will see that it looks a little bit like that. So I define a two-time correlation function of t and t prime. In this way, I do 1 over n, sum over I, sigma I of t, sigma I of t prime, and then I do an average. This average is now over the dynamics. Which means I have to specify the initial condition of the dynamics, and then for a given initial condition, I run this Langevin dynamics, and there is some noise. This is a white noise, so it's random. And so the average is over the realizations of the noise and over the initial condition, okay? So this is what I mean by a dynamical average. But still, this dynamical average depends on the J, because the initial condition might depend on the J, it depends on what I take as initial condition, but again, the Hamiltonian that I use to run my dynamics depends on the couplings J. So then, again, for convenience, I can take an additional average over the J. And I don't have much time to really discuss this in detail, but some of you ask me questions and you can keep asking questions. But the idea is that this correlation function, which is a global average over the spins, will not be very different for one realization of the J and from one to the other realization of the J. So if I take an average, it's representative of the value of this thing, okay? So essentially, there are no fluctuations of this object in the thermodynamic limit, so it will coincide with its average. And taking the average is convenient to do calculations, because if you don't take the average, you have this disorder that you have to deal with, and it's difficult because it breaks any kind of symmetry in the problem. And while if you take the average, you will, I mean, you have to do the calculation to see that, but you... Anyway, if you don't like this average, just think that there is no average, and this is, in the thermodynamic limit, this doesn't fluctuate from system to system. Okay, yes?
Sorry, can you say again what that mu means?
Yes, so mu, we will compute it explicitly in a moment, but it's just imposing the fact that the spin must be on the sphere. So I want the sum of sigma I square to be equal to n, which means if I take a derivative, d over dt of this thing should be 0. And if I take the derivative of this, what I get is, this is going to be sigma I, well, 2 sigma I times d sigma I over dt, right? And this must be 0, which means the gradient, the time gradient of sigma must be orthogonal to sigma, which is reasonable because you want to stay on the sphere. So the time derivative of sigma must be orthogonal to sigma. So what do I do to enforce that? I add the Lagrange multiplier, and the Lagrange multiplier is proportional to sigma because I want to remove the longitudinal term in the gradient. So I just have to decide the value. Mu is a number that I have to define. The only problem is that when there is noise, mu depends on the noise, so then you have to work a little bit more. I will give you the expression of mu in the zero temperature limit when there is no noise, that it's much easier, just to save time. But yes, okay, so that's the thing. Now, we want to start, so this is a good quantity to measure, and just to write it in a more intuitive form, we can write it in this way. So if I define sigma hat as the unit vector that is parallel to sigma, so sigma hat is just sigma divided by square root of n, right? Because the norm of sigma is n. So if I divide by square root of n, I get sigma hat, that is a unit vector. This correlation function is just the scalar product of the direction of sigma at time t with the scalar product at time, the scalar product of sigma at time t with sigma at time t prime, of the orientation of the vector. And I want to take the average over the dynamics and then the average over J. Now, I want to start by the equilibrium dynamics. Yes?
You said average over the dynamic. What do you exactly mean, since we have already two times which are given in the
Yes. So the idea is I have to specify the initial condition. So let's do the equilibrium case so that in the equilibrium case, I want to draw the initial condition sigma 0 from the Boltzmann distribution. Okay? So I draw an initial condition sigma 0 from the Boltzmann distribution, and then I run, of course, I draw it for a certain, I choose my couplings. The couplings are chosen at the beginning and they're fixed. So I choose my couplings, I draw an initial state from the Boltzmann distribution, and then I run the dynamics. The dynamics depends on the noise. So I will get a trajectory. This vector starts moving on the sphere. Okay, let's imagine this is a three-dimensional sphere, so it's going to move somehow around, okay, on the surface of the sphere. So this is a trajectory sigma of t, okay? Right? This trajectory depends on the initial condition and depends on the noise. So then I measure sigma at time t, I measure sigma at time t prime, and I take the scalar product, and I take an average over trajectories and over initial conditions. Is that fine? Now, if my initial condition is drawn from the Boltzmann distribution at temperature T, and if I run Langevin dynamics at the same temperature T, then the system is always in equilibrium, right? Because the Langevin dynamics is described by the Fokker-Planck equation, and the Boltzmann distribution is a stationary solution of the Fokker-Planck equation, so it doesn't evolve. So if P of sigma 0 is this, at any time t, P of sigma t is going to be this, which means that everything is stationary. So in particular, my correlation function depends only on the difference of the times, because I can shift time as I want, right? Because at any time t, the state is described by the same Hamilton, the same distribution. So I have in this case a single time t, and I can write this as sigma of t scalar product with the initial condition, for example. Okay, how does it look like? So you can compute this object exactly in the thermodynamic limit by using this dynamical mean field theory. So you start from the many-body dynamics, and you work out a mapping of this into a single variable. So you have n components of the vector sigma here, but you can see that you can write this in terms of one single component that evolves in a thermal bath given by all the others. And then you can close these equations, and you get a closed integral differential equation for this C that has the form like derivative of C with respect to time equal to some integral where there is C, okay? I can maybe, well, in equilibrium, I think it's, I mean, I don't remember it by heart, but it looks like something like integral between 0 and t of c to the power p minus 1 times c dot, something like this. Okay, so it's a simple equation, closed. It's not exactly this, but something like this, okay? And you can solve it. Well, you cannot solve it analytically, but it's a simple equation that you can put in the computer and solve it. So now let's plot this correlation function versus time. So now, at time equals 0, this correlation function is 1, right? Because sigma hat square by definition is 1. And what we expect is that at long times, if the system is ergodic, it will diffuse, the vector will diffuse on the sphere, and it will reach a state that is typically orthogonal to the initial one. Again, because if you maximize the entropy on the sphere in large dimensions, you see that you want to be on the orthogonal space. So what we expect is that this thing will go to 0 at large times. So how does it look like? Well, if you, I mean, okay, in the notes, in these notes, there is a figure that shows it, and I mean, you can compute it numerically over very, very long times. So let's put a logarithmic scale here, just to have a big range. I mean, you can compute this over 12 decades quite easily with modern computers. And what you see is that for high temperature, this is something that looks like an exponential. It decays fast. So this means, well, this system will quickly diffuse and start exploring all the sphere. When you lower the temperature, you start to see that it slows down. And at some point, you start to see something like this. And then it becomes even slower, until at some point, it becomes infinitely slow. I mean, it doesn't relax to 0 anymore. And you get a finite limit. By the way, if you call Q, for reasons that will be clear in a second, the long time limit of this object, sorry, and you look to the equation for C, so if you take the long time limit, assuming that there is a finite limit, so I mean 0 is always, okay, let me say it in another way. If you call Q this limit and you assume that it is non-zero, and you take this equation and you write it in the limit of infinite times, then you get an equation for Q that is very simple. It has this form. Okay.
Q as you presented is the L mode and S.
Yes, I will. It's the same thing. Here is not C to the P minus 1. It's actually, in general, it's F prime of C of T minus S, where F is this function, here. You remember F was, this is not very important, but F was 1/2 sum over P of alpha P Q to the P. So in general, it's a function that depends on the couplings. So from this, in the long time limit, you get an equation for Q that is given by this expression, beta square F prime of Q is equal to Q over 1 minus Q. Okay? Now, So this is a very simple equation that you can solve in many different ways. And what you see is that above a certain temperature, there is no solution of this. Here I divided by Q somehow, so Q equals 0 is always a solution. So at high temperature, the only solution, the only possibility is Q equal to 0, so you decorrelate completely from the initial condition. But below some temperature that I'm going to call I want to follow the notation. This has different names in different communities. I will follow the notation of the glass community that calls this the mode coupling theory temperature for historical reasons. Otherwise, sometimes it's called the dynamical transition temperature, so it's called TD. I mean, it's the same. Below this temperature, you get a non-zero solution for this. Okay? What does it mean to have a non-zero solution? It means, I can maybe, it means that asymptotically, the vector sigma at large time has a finite scalar product with the initial one. So it means if I start here, I don't diffuse everywhere. I remain stuck in a finite cone around the initial state. So I start here, I start to move, I move. But I remain in a region that has a scalar product Q with the initial state. Okay? Now, I erased the Edward Anderson order parameter, but what happens, I mean, why I call it Q? I call it Q because it's essentially the same as the Edward Anderson order parameter. Why? Because, you see, if T is very large, I can think that somehow sigma of T and sigma of 0 are uncorrelated realizations of the Gibbs measure, right? Because I expect somehow that if time is very large, I should lose somehow the correlation. It's not completely decorrelated, because if it was completely decorrelated, it would go on the orthogonal space, but I can still think that this is something like sigma of T, sigma of 0, where I'm replacing the dynamical average with the Boltzmann average. And this was my definition of the Edward Anderson parameter, okay?
In this case, how do the dynamical temperature compare to the TK?
Yes, exactly. That's the problem. Because I told you that if I do before that if I do a calculation of the Edward Anderson order parameter from the thermodynamics, from the Boltzmann measure, I have a jump at Tk. So I get something like this. This is 1, this is the glass, and this is the paramagnetic state. This is the outcome of the replica calculation. Now I can do a dynamical calculation, and I get something similar. So I get Q equal to 0 above this temperature TMCT, and I get Q positive below, and it has a jump, except that TMCT is bigger than Tk. So what you can show is that you get something like this. Here you have a square root like singularity, and you have a jump. So what's going on here? This is very strange, right? So people were puzzled for a long time until they understood what was going on.
Sorry, before you go there, can I interrupt? So
Yes.
I'm quite confused. So how did you get this equation at the bottom here?
This one?
Yes.
No, I didn't derive it. I told you it can be done, but
And is it really C dot on the left and C dot on the right?
yes.
Okay, and then how do you go from here to the top one?
Yes, I also didn't do it. It's a little bit of work. So to obtain this from Langevin, there are many different ways. Essentially, what you want to do is to study how one of these sigma is coupled to all the others. Because this Hamiltonian is a fully connected one, each of the sigma is connected to all the others. So this force here is a sum of many, many terms, order n to the p minus 1 terms. So let's say if p equal 2, if you are doing the two-body term, this is a sum of n terms. When n is large, you can essentially replace this by its average. So you get a single particle process for each of the sigma, except that you have to compute the average of this. It's not only the average, there is an additional term that is the response of this, so you have to work it out a little bit, but you can self-consistently compute this average as when you do mean field. You know, when you do mean field, you say, okay, I have my spin that is coupled to all the others, so it will feel a magnetic field that is the magnetization of the other spins, and then I impose the self-consistency and I close the equation and I get m equal to hyperbolic tangent of m. Here you have to do the same, except that your field is time dependent and you have to close the equation. When you close the equation, you see that you get this. And then how you go from this to this, that's easier. If you assume that there is a long time limit, then this term goes to 0 because, and here you have to do an integration by parts. You have to work, because
you would say that the right hand side also.
yes, but there is this term that this is an integral. So you have to work it out a little bit. You do an integration by part and you will get to there. It's just, yeah. Okay, so now the puzzle is what's going on here. I will give you, again, a descriptive answer, but the solution, okay, maybe I can write here. So now again, I cannot do the calculation, it would take a lot of time, but the solution is the following. Okay, let's redraw this thing. So when t is very high, so for t bigger than td, or sorry, tmct, I call it tmct, what happens is that I start from some sigma 0, I run the dynamics, and the dynamics will go everywhere. When t is smaller than tmct, what I know is that thermodynamically speaking, the system is a paramagnetic system. So if I look to the Boltzmann distribution, if I draw two configurations from the Boltzmann, they typically have 0 scalar product because thermodynamically the overlap is 0. The Q is 0. So we have seen that if you do the thermodynamic calculation, you get this. Okay, this is the thermodynamics, and this is the dynamics. So this means that if I take two configurations at random from the Gibbs distribution, one is here, and the other one is going to be essentially orthogonal to the first one. And then if I draw a third one, it's going to be orthogonal, and they are all orthogonal because there is so much space. This is in the thermodynamic limit. So these are when I do the dynamics, these are two independent initial conditions for my dynamics, because I was telling you that the dynamics is initialized in equilibrium. But then when I run the dynamics, this one is going to evolve, but it's not able to decorrelate. It's going to be stuck in a region. This one is also going to move, but it's also not able to decorrelate, so it's stuck in another region. So I have these cones on the sphere that trap the dynamics. So each of them is a metastable state. Okay? The point is that if I now draw a third initial condition, it will be orthogonal to the first two. So there will be another cone. So there are many of them. Okay? How many of them do I get? And well, this requires another calculation that you can do, but you have to use a bit more advanced methods. But in the end, what you find is that the number of these metastable states is exponential in the size of the system, with a prefactor, sigma, that depends on temperature. So above the MCT, the system is really paramagnetic. The dynamics can decorrelate. You are ergodic. Everything is fine. Below TMCT, it looks like the system is paramagnetic. Why? Because there are so many states that if you draw two configurations at random from the Gibbs ensemble, one is going to be in one of these states, the other one is going to be in another state, and they are typically orthogonal. So if you look to the magnetization of the first one and the magnetization of the second one, and you take the scalar product, it looks like they are completely independent. So it looks like the system is paramagnetic, but actually if you run the dynamics, you realize that it's a non-ergodic paramagnetic system. Okay?
The sphere is n-dimensional.
Yes.
How can you have more than n orthogonal cones?
Because the volume of an n-dimensional sphere is exponential in n, essentially. The surface, let's say. I mean, imagine that.
Are not orthogonal.
Huh?
The cones are not orthogonal.
Well, yeah, they are orthogonal. I mean, if you take two at random, they are orthogonal. It's again, yeah, I mean, intuition in high dimensions is not very good. But so you know, think maybe you are more familiar with the Ising spins. So if you have Ising spins, they are plus minus 1. You have 2 to the n you have n spins and 2 to the n configurations. So if each of these cone involves a subset of configurations, you can have exponentially many cones. Now, the fact that they are orthogonal, it's a probabilistic statement. I mean, you have a distribution of overlaps. And if you take two at random, they are going to be orthogonal for entropic reasons. So actually, yeah, maybe it was a bit misleading. They are everywhere, but there are so many that if you take two at random, they are going to be orthogonal. So thermodynamically speaking, two configurations that fall into different cones are typically orthogonal. Yeah, sorry for the...
Here you say that you are using to start with configuration that you are drawing from temperature, which is the same temperature as the one you are
Yes.
to probe the dynamic.
Yes.
Now, if you want to prevent you are falling into one of these traps, can't you just draw a state totally at random at the sigma 0, and then look at a dynamic between two times. Because if you do this, you are less likely to fall always into the same trap. And so you can expect maybe to probe a larger subspace. Since you are
Yes.
less
Yes, that's the next thing I want to do. So start from a random configuration and quench to low temperature. But you will see that you will explore a large space, but you will never be able to equilibrate. Let me get to that a bit slowly, because, so let's finish this. This is, I assume that I can start in equilibrium and I run equilibrium dynamics. The advantage of doing that, the reason why I do that is that in this way I only have one time, okay? Everything is time translational invariant, so I only have to deal with one time. To do what you want to do, I have to deal with two times, so it's going to be slightly more complicated. But so so at high temperature we have this situation, at low temperature we have this situation, and so what's happening at TK? What's going on at TK? Well, what's going on at TK is that if you compute this object, which is somehow the entropy of these states, how many states, it's the logarithm of the number of states that you have. If you plot it here, this will jump to a finite value at the mode coupling point, and then it goes to 0 at TK, and it's 0 again, in all the temperatures below TK. So what does it mean? It means that when you reach TK, the number of these cones is not anymore exponential in n, and with a little bit more work you can show that it is actually a finite number. So now the situation becomes more like what you get in a ferromagnetic system. In a ferromagnetic system you have two states. In this kind of glasses you get maybe 15 states. It actually depends on the J. So if you draw one system, maybe you get 15 states. If you get another system, maybe you have 12. There is a distribution, but it's finite. If it is finite, it means that if I now draw two configurations at random from Gibbs, one of them falls in one state, the other one falls in another state with probability 1 divided. So if I have k states, the probability to get different configurations, different states, is k minus 1 over k, right? And the probability to stay in the same state is 1 over k. So if I draw two configurations and they explore the states at random. So in the ferromagnetic case, if I draw twice a configuration from the Gibbs, there is a probability 1/2 that they are in the same ground state, and the probability 1/2 that they are antiparallel. Here there are k states, so it's 1 over k, but if k is finite, this is a finite number. So Q is going to be finite even in the thermodynamics. So this is why Q is finite here and it's 0 here. Here it's 0 because I have an exponential number of states, and so the probability of finding twice the same is exponentially small.
Sorry, can you repeat what type 1 over k and k minus 1 over?
Sorry, yes. What I'm saying is that when I am below this Kautzmann temperature, the entropy of the states, of the metastable states, goes to 0. And so here I have exponential of n sigma states, and here I have k states. Maybe k is not, it's not the same k as tk, but okay. I have, I don't know, p states. No, p is probably m states, I don't know, whatever. I have a certain number of states. Okay, let's call it k. I like k. Sorry. So, but this k is a random number. that depends on J. It has a certain probability distribution, and but the important point is that if I draw twice in this region, if I draw two configurations from the Gibbs measure, the first one falls in one of the K states, and the second one, what is the probability that it falls in the same state? If they are all of the same probability, it's 1 over K. So 1 over K is the probability that two configurations that I draw from Gibbs fall in the same state. You see? So like if you have a ferromagnetic system, in a ferromagnetic system, the free energy is like this. There is the plus state and the minus state. If you draw one configuration at random from the Gibbs measure, it will fall with probability 1/2 in the plus state, with probability 1/2 in the minus state. If you draw a second one, no, because the first one decides the state, I don't care. Now the second one has a probability 1/2 of, okay? So it's K times 1 over K square, okay? So what you have to imagine is that in the glass, in this region here, your free energy has, if you do again this cartoon that I do all the time, you have K states. So the first replica, the first copy goes here, the second copy has a probability 1 over K to go here, and the probability K1 minus 1 over K to go in another one. Yes?
But now you are considering only equally stable states.
Yes. I'm doing that because thermodynamically, if I look to the thermodynamics, the probability of a state is exponential of minus f and times n. So I mean, only the states with the same free energy contribute. Actually, okay, yes, if you want to be more precise, you have to, they can have different weights, but the argument is the same. If there is a finite number of states, the probability of finding twice the same is finite. The point is that the big difference is whether this number is non-zero or 0. If it is non-zero, then the probability of finding twice the same state is exponential. Exponentially small in n. Yes?
What is happening to this number above TMCT?
So above TMCT, there are no states anymore. So no metastable states, they all become unstable and disappear. And there is only one state, which is the paramagnetic state. So what happens at TMCT is more like what you are used to see in a first order transition. So in a first order transition, you can have two states, and when you raise temperature, this one can become unstable, and then you are left with only one. So it's similar somehow. So they all become unstable, and you just get one big state that is the.
And in some sense, what is the difference between this kind of region and the hysteresis phenomenon that arise in first order transition?
So you
also get trapped close to a local minimum and you don't relax for a very long time.
Yes. So there is hysteresis and memory in glasses in these systems, but this requires a discussion of out-of-equilibrium dynamics, and well, it's a bit tricky. But yes, there is hysteresis. So you can see that there are these states. So if you manage to get into one of them, then you will see that there is hysteresis because you will stay. The problem that we have to discuss next is how do we manage to get into one of these states? Because, should I stop now or in, I don't know, in 10 minutes? Or 10 minutes. So the point is that now there is, what you see is that my assumption, I did all this assuming that I start in equilibrium and I run the equilibrium dynamics. And so I told you, okay, if I am at high temperature, I decorrelate. If I am below this MCT and I start in equilibrium, I will remain close to my initial state. And so then you should say, okay, well, but this means that reaching these configurations is hard, right? Because the dynamics, if I assume that I start in this state, I will stay next to the initial state forever. So this means that there is a big trap. So how do I get into this state? And so the question is, either you have some very smart trick to prepare the initial state from the Boltzmann, or you would do Monte Carlo or Langevin. And what do? Usually is something like simulated annealing. So you start at high temperature and you start to go down in temperature, okay? And the problem is, how does the relaxation time look like? So I can ask, okay, I start from high temperature, I start running my dynamics, and it decorrelates, it's ergodic, everything is fine. Let's define a time scale that is usually called alpha time in the glass literature. That is the time is on the horizontal axis. Let's ask how long does it take to decorrelate? So to reach, for example, a correlation of 0.2, I don't know, 0.2, for example. So this is what is called the alpha time. It's called alpha because, as you see in this plot, there is another time that is the time to reach this plateau. So there are two time scales, and this one is called beta time for historical reasons. Anyway, let's forget for the moment about the beta time is the time you need to explore the cone. But what we're interested in is the time to really decorrelate. So I can plot the shape of this time as a function of temperature. And what I get is something like this. So this time is divergent at TMCT, as you can expect from there. It's going to infinity. And it's actually going to infinity as a power law with an exponent gamma that you can compute from the theory. It's interesting because it's a non-universal and non-trivial exponent. It's not like 1/2 or something like that. It's an irrational number that depends on the system. But anyway, so it's a power law. And so the point is, if I try to do simulated annealing, so I start from a high temperature, I equilibrate, I go down a little bit in temperature, I equilibrate. It requires more and more time until when I get sufficiently close to this temperature, I cannot equilibrate anymore in a finite time. The time that it takes to equilibrate goes to infinity. So this means that I cannot equilibrate below TMCT, at least not by cooling from high temperature. So it's nice to know that if I were able to equilibrate below MCT, then I would get this stationary correlation with an infinite plateau, but I'm not going to get there by cooling. So how do I do that? I mean, you cannot do that. That's why you cannot equilibrate a glass. And so what you're left with is non-equilibrium states. So now we have to understand the non-equilibrium states, okay? The last thing maybe I can say before I'm running quite late with respect to my initial plan, which is good because it means you're asking a lot of questions. So I wanted to finish the out of equilibrium today, but I will do it tomorrow, which means that maybe the other toy model will be discussed a bit fast, but it's fine. So let's stop here. Just the last thing I want to say is what happens when n, this is in the thermodynamic limit. So this curve here is for infinite system. What happens when n is finite? Well, I told you that if n is finite, you can always equilibrate. The problem is that in order to equilibrate, you have to visit somehow a reasonable number of these states. And what you can see is that these states are metastable, and the time it takes to jump from one state to the other is exponential in n. So you have a time, so the time to equilibrate, the alpha time is finite when n is finite, but it behaves like this. And so when you increase n, it's going to converge to the finite limit above TMCT, but it's going to diverge exponentially with a certain prefactor that we don't know in n when you are below TMCT. So this once again it means if you want to equilibrate below TMCT, it takes a time that is exponential in system size. And so in particular, if you want to find the ground state by simulated annealing, it means you want to be in equilibrium down to 0 temperature, and in this system it will take an exponential time in n. Okay? So I guess we can stop here. So tomorrow I will do what you proposed, which is start from a random configuration, cool down the system, but not, we know that we cannot stay in equilibrium, so we will cool at a finite rate, or even directly to 0 temperature, and try to see what happens in that case. And yes, the short answer is that what happens is that the system is able to explore somehow the sphere, but in an out of equilibrium way, and there is a non-trivial dynamics of exploration well, that we will discuss tomorrow. Okay.
All right. Any questions?
Sorry, maybe I missed something, but why could glass the third part of your thing and not the second?
Yes, you are right. So yeah. So this phase is also a glass, but just to distinguish it from the other one, we usually call it a dynamical glass, in the sense that if you do thermodynamics, the system looks paramagnetic. It doesn't look like a glass. You have to do the dynamics to see that it's a glass. If you take equilibrium configurations, if you had, if I give you a super powerful computer that can do everything, and you use this super powerful computer to generate equilibrium configurations, and you look at them, you will not see that the system is a glass. They look like paramagnetic. They are everywhere. They are well distributed on the sphere. So the only way to see that the system is a glass is that you take one of these equilibrium configurations, and from there you run the dynamics, the Langevin dynamics, so it should be a local dynamics, let's say. And then you will see that each of these configurations is actually surrounded by a trap that blocks the dynamics. But there are so many of these traps that if you don't do the dynamics, it looks like a paramagnet. It's very strange. It's very strange. It looks very exotic. So you might wonder why I'm so interested in this thing. But actually, when you apply it to these problems like coloring or classification, you see that this is it's really the hard phase. This is where it starts to do things. Because here, it's true that, I mean, well, in this in the thermodynamic glass phase, it's hard, but at least there is some information. In the sense, okay, this is a bit, I mean, if you're doing, okay, this is a bit hard to explain quickly, but like, there are many problems where you hide the signal, and there is a signal and there is noise. And you want to recover the signal. So the signal is the minimum of some cost that depends on the noise. So the signal is typically one of these cones. So if there are a finite number of cones, it means that there is a probability to find the signal. If there are exponentially many cones, and the signal is one of them, even if you were able to sample, you would never find the right signal. So this is really a phase where, from the information theory point of view, there is no way to recover any information. And so that's why people, and it happens generically in many problems like the ones that I listed. So that's why I'm spending time on it. Sure.
But maybe you could answer. Okay.
So I just have a quick question, but when people do numerical examination of such a system, they sometimes use the so-called parallelism,
Parallel tempering.
annealing in
Yes.
order to be able to jump from one configuration to one totally other configuration
Mhm.
by jumping between parallel dynamics. Can it be a method to prevent this dynamical freezing of the dynamic?
No. So in this kind of systems that have this kind of transition, even if you do parallel tempering, it will not work, because in parallel tempering, what you do is that you have many copies at different temperatures, you evolve them in parallel, each of them is running the dynamics at its own temperature, and from time to time you switch two of them. And the problem is that, this transition is so sharp that, it will not, you will not accept the exchanges in the vicinity of TMCT. The parallel tempering works when you have a continuous transition, like in the P equal 2 case or in the Sherrington-Kirkpatrick model, where this Q has no jump and there is no complexity. So there is a class of spin glass models where the transition is different. There is no distinction between, there is no hard phase. It's a continuous transition, and in that case, parallel tempering works much better. So these are easier problems. That's why even if they're still.
In the gas phase, the number would be minima of the potential depends on J, you said. But
Yes.
how do they scale with the size of the system?
It's finite. It doesn't depend on the size in the thermodynamic limit. So there is a distribution, it's like an exponential distribution with some parameter, and so it's a finite number. There is one thing I forgot to say. If you want to get a bit of intuition on this TK, there is a model that is called the random energy model that you can solve without replicas just by doing extreme value statistics. And in the random energy model, there is TK, and you can compute this sigma explicitly, and you can compute everything. And so if you want to do that, you send me an email, I send you a link to an exercise that we teach in our course in Paris that you can do. It's a simple exercise. I can give you the exercise and the solution, and you can try to do it. And you can compute TK, and you can get all this in a simple way. So this can be a good exercise to do if you have time.
Other questions?
Before you said that the transition is kind of restored there and kind of
Yes. Why I say yes? So it's first order because the order parameter has a jump, and because there is metastability and hysteresis, as you were saying. So there are all these states that compete, and if you get trapped in one of them, then you stay there, so you can see. But it is second order from the thermodynamic point of view. So if you look to the energy that I erased, the energy is continuous at the transition. I had the drawing, but it looks like that. Energy temperature, it's like that at TK. So what happens is that the specific heat has a jump. So from the point of view of classification of phase transition in terms of singularities of the derivatives, it's a second order. It's kind of an accident, and actually if you do the REM, the random energy model, you see why. Basically because, again, because this singularity, this jump in the order parameter, doesn't give you a jump in first derivative of the free energy because there are so many states that it will cancel somehow the jump. So if you look to all the first derivatives of the free energy are continuous, which is important because, for example, in glasses, it is known that at the glass transition, when the system goes out of equilibrium and becomes a solid, the specific heat as a jump, but the energy, the volume, all the first derivatives are continuous. So that's one reason why people started to think that maybe these are good toy models for glasses. Because the glass transition looks like a second order transition. It's a non-equilibrium, but looks like second order. Okay.
Other questions?
This afternoon I'm around, so if you want to ask other questions offline, just send me an email or I will be in my office.
Do we have a question session this afternoon?
No, tomorrow.
It's tomorrow.
Tomorrow afternoon lectures.
So maybe just one quick question. So what it says to get this identity that the large time limit of C of t is q. This is keeping n finite. You need to keep n finite.
No, sorry. No, all is done first taking the thermodynamic limit.
It's first the thermodynamic limit.
And then any other thing, because this the equation I raised, the integral differential equation for C of t, that is correct in the thermodynamic limit. In the thermodynamic limit.
But this identity over there, no, this one, the left one.
This one?
Yes.
This is only in the thermodynamic limit, because in finite size, it will always relax to equilibrium over an exponential time. So yes, so this is, to be correct, this is first thermodynamic limit, then time going to infinity. It's the usual thing. You cannot have any phase transition in finite size. So if your size is finite, everything is going to be ergodic and relax. So this correlation function will go to 0 over, but the time it takes grows exponentially in n.